6.7 Newton's law of cooling. Newton's law of cooling allows us to find the temperature at which perhaps a cup of coffee cool after sitting in a room for so many hours. Or it can also help us find the time of death of a person, given that we know their current body temperature. We can actually work backward and solve and figure out how long a person has been dead. So the way how Newton's law of cooling works is the change in the temperature with respect to the change in time equals to some constant times the temperature minus the surrounding temperature. This is the differential equation that describes the rate at which the temperature is changing. And the solution is the current temperature at any time can be found by taking the surrounding temperature plus the initial temperature minus the surrounding temperature again, all multiply with e raised to the kt. All right. Say if I had a cup of coffee and I just took it off the boiler, I leave it in the room to let it cool. The question is, if I want to know, if I leave it there for, let's say, 10 minutes, what will the temperature be? And this equation gives me that answer. Or let's say if it's currently 130 degrees Fahrenheit, perhaps I want the temperature to go down to maybe 90 degrees, then what is the time? How long should I wait until the temperature goes down to 90 degrees? And that can be found by solving T for this equation. So let me show you how we can perhaps find the solution from this differential equation. So starting with the differential equation, we solve for T using separation of variables. I start by multiplying everything by dt. So d of t equals to k times t minus t sub s d little t, because I multiply both sides by d little t. D little t stands for the change in time. D capitalized T stands for the change in the temperature. I am going to go ahead and divide both sides by T minus Ts. So 1 over T minus T sub S dt equals to K dt. Integrate both sides. When I integrate both sides, this integral is going to give me 1 over anything is likely going to give me ln. So this integral is going to give me ln. So we have ln of t minus t sub s. This integral over here is going to give me k little t plus c. And again, to get ln here, we're going to have to do a u sub. Let u equals to t minus t sub s. And remember that t sub s is a constant. Raise both sides by e. This is going to, so I'm going to raise both sides by e like this. The left side gives us t minus t sub s. The right side gives us e to the kt plus c. And remember that this becomes e to the kt like this times e to the c, and e to the c is another constant. So let's call that c. like that. So e to the c is a constant, and I just chose to put it in the front, like this. And now I'm going to go ahead and replace, add t sub s to both sides. So t equals to t sub s plus c e to the kt. Again, just to summarize what we're trying to do here, we're given a differential equation. This is how an object cool. Knowing to figure out how an object cool, we need to know how the change in temperature works. Isaac Newton gave us his law of cooling, which says that the change in temperature with respect to the change in time is always equal to a constant times the differences in the current temperature and the surrounding temperature. So this is how an object cools. This is the rate at which the temperature is decreasing or increasing. By solving this differential equation, we can easily figure out the temperature of the object if we know time. So that's what we're doing. We're trying to figure out the solution to this differential equation to give us this formula. The next thing I do after I get to here is I plug in my condition, and my condition is the initial temperature. So at time equals to 0, we're gonna let at time equals to 0, we're gonna let T naught represent the temperature. T naught represent the temperature at time equals to 0. So if I plug those into my equation, then I get T naught. So here is my equation. Here's my general equation. I plug T naught in here. So T naught equals to T sub s plus C e to the k times 0, because we're talking about initial temperature. Solving for C, C would equal to T naught minus T sub s. Now, if I replace what C is, then I get my unique solution or my particular solution. So replace C with T naught minus T sub s. That means that the temperature at any time can be found by taking the surrounding temperature plus T naught, which is your initial temperature, minus the surrounding temperature again, times e raised to the kt. So in order to find the temperature at any time, in addition to knowing what time is, we also need to know what the surrounding temperature is, and we also need to know what the initial temperature is. So like, for example, if I took this cup of coffee off a boiler, I can find the initial temperature by sticking a thermostat in here, and perhaps that will give me a reading of 130. I can look at my thermometer in the room to determine what the surrounding temperature is, and that will give me these two values. And if I know time, if I want to know, hey, if I let it sit for 10 minutes, what would be the temperature after 10 minutes? So solving for this T will give me that. But in addition to finding the temperature 10 minutes later, I also need to know K, which is what we call an experimental constant. So we have to do some work to find what K is before we really can find what the value is. Giving you a graphical look at what the temperature, the cooling will look like. Usually here is time. Initially, the temperature is going to be really warm, but over time it's going to cool off. And then cool off, and it's going to level out. It's going to level out, but it's never going to dip below the surrounding temperature. So that would be kind of like a graphical look at how an object cools over time. Let me go ahead and mention some notation here. The initial condition is t at time equals to 0. T naught represent the initial temperature, and then T sub S represent the surrounding temperature, which is the temperature that's currently present in the room, and T naught represent the initial temperature, the temperature at which the perhaps cup of coffee is at when it is first poured into this jar. Let me walk you through a problem. Let's say a pot of liquid is put on a stove to boil. The temperature of the liquid reaches 170, and then the pot is taken off the burner. So immediately when it was taken off the burner, that's when time started, so time equals to 0. The temperature at time equals to 0 is 170 degrees Fahrenheit. It is taken off and is placed on a counter in the kitchen. The temperature of the air in the kitchen is 76. That tells us that our surrounding temperature is 76 degrees. Okay. After 2 minutes, the temperature of the liquid in the pot is 123. So this is our experimental value. Okay. 2 minutes later, the temperature is 123 degrees Fahrenheit. We're going to use this additional experimental information to help us find out what K is. So the question here is, how long before the temperature of the liquid in the pot will be 84 degrees Fahrenheit? So we want to know the time so that this is equal to 84. So ideally, here's what we're doing. We're gonna plug 84 degrees into here. We're gonna plug 76 into here. We're gonna plug 170 into here. 76 goes in here again, times e to the k, and then we have to find out what time is because we're looking for time. So there are goods and bad. The goods is we know this value, we know that value, we know this value, we know that value. The only thing we don't know is k. So we know k, then we can find out what time is. So the first thing we do is we find out what k is. To find out what k is, we start out by plugging everything we know in there, and we're going to try to solve for k. So step 1, we're going to go ahead and replace the initial temperature, which is, but let me go ahead and write down the formula first. So T temperature at any time is the surrounding temperature plus the initial temperature minus the surrounding temperature again, e to the k t. All right. So what we're going to do now is we are going to find k, and to find k, we're going to plug our experimental value in. So use experimental data to find k. And this is our experimental data. So the temperature is 123, so 123. Surrounding temperature is 76. Initial temperature is 170. Surrounding temperature is 76. E to the k, and t is 2. 123. Clean this up. We're gonna get 76 plus 94 e to the 2k. This is gonna gives us 47. 94 e to the 2k. So we get 47 over 94 e to the 2k, and then we ln both sides, then we're going to get ln of 47 over 94 e to the 2k. So by solving for k, it's going to equal to ln of 47 over 94 divided by 2, so that's k. Alright? So once we know k, then now we can answer the question, because that was what was missing in finding the answer to this question. Now, I am going to plug everything I know in here, and I'm going to solve for t. So, how long? So, find time. Until temperature reach 84 degrees. I am gonna plug 84 in here. I'm gonna plug 76 in there because surrounding 76. Plug 170 in for the initial minus the surrounding, and then e to the k t, and I know what my k is, and we're gonna deal with that later. Cleaning this up, we are gonna get, simplifying this a little bit, okay? So subtract 76 to both sides, you get 8. Subtracting this, we're gonna get 94 e to the kt. Remember, we know what k is. Dividing both sides and simplify, we get 4 over 47 equals to e to the kt. ln both sides. ln this side is going to give us kt, and then we solve for we solve for time. So time is going to equal to ln of 4 over 47 divided by k. But remember, k is this number. So find out what k is, and then we're going to divide. So let me go ahead and use a calculator, and we'll finish this problem up. So first I'm going to find out what k is. ln of 47 divided by 94, and then divide that by 2. K is negative 0.346, and so save that. Let's save that. Let's store that as the letter. So let's take our answer, store it as the letter x. So we store that as the letter x. To find time, I'm just going to take this divided by k, but remember the k value is stored as the letter x. ln of 4 divided by 47 divided by k, which is stored as the letter x. And this tells us it is 7.109. So t equals to 7.109. In other words, about 7.109 minutes later, the temperature will go down to 84 degrees. See you guys next time in class.